All right, let's talk a little bit about the dot product. This is not going to be a comprehensive video on the dot product. This is just an introduction with the most basic and important properties. And, if you need more, you can find other videos about that, but this should be enough to get you started to understand more or less what it means and how to compute the dot product algebraically directly. So what the dot product is a way to multiply two vectors. For real numbers, there's only one way to multiply them. You just multiply them using regular multiplication. But if you have two vectors, there's more than one way to multiply them. In fact, in our three, there are two main ways. There's the dot product, which is this one, and there's also the cross product, which I'll talk about on a separate video, also about basic properties that it has. But let's stick with the dot product for now. So the way to calculate the dot product is very simple. What you do is you multiply the x's of the two vectors. So you have vector u, which is x1, y1, z1, and vector v, which is x2, y2, z2. What you do is you multiply x1 with x2, so that's it, that right here, and you add that to multiplication of y1 and y2, and add that to the multiplication of z1 and z2, right? So multiply the x's, multiply the y's, multiply the z's, add those three. So unlike what happens with real numbers, this is going to be a number, right? It's not a vector. Okay, so with real numbers, you multiply two numbers, the answer remains a number. But with vectors, you multiply two vectors, the answer doesn't remain a vector, right? As long as we're talking about the dot product. So you do the dot product with two vectors, the answer doesn't remain a vector, it is a number also. So we lose some of the information that the vectors had. There's no direction anymore in the answer. But that still has important properties. Let's first calculate the dot product here. U dot v will be -1 times -3 plus then -2 times 0 plus 9 times -1. And then the rest is just algebra, so +3 plus 0, actually arithmetic, right? -6. So that is the dot product, okay? This is the first time I'm showing a multiplication, a dot product of two vectors. When I say the words dot product, and anybody else does too, you have to know that this is what they mean, okay? Now let's talk about, this is super simple, it seems useless, pointless. Let's talk a little bit about what it does and what it's for. So some of the deep geometric implications. This first one is not so deep, it's kind of shallow actually, but if you have a vector u that's x, y, z, and you compute the dot product of u with u itself, that will be x times x plus y times y plus z times z, right? So just multiply x with x. U and v are the same, and this will be x squared plus y squared plus z squared, which will be the magnitude of u squared, right? For you to get the actual magnitude of u, you'd have to take the square root of that, but this is the formula they end up with. Multiplying a vector, dot product of the vector by itself, does give you its magnitude squared. So that's the first connection. The right side of this is geometry. It's the length of the vector, and the left side is just the dot product, which is just some algebraic thing that we learned how to do. So I think that's already some interesting geometric connection between the dot product and the geometry of the vector, as I've said. Now, something a little deeper, something a little bit more interesting is how to find angles, okay? Let's begin by talking about this. This is a formula. You can prove this. Maybe I can give you a taste of how to prove it. But with this formula, first of all, what's it saying? Left-hand side is the dot product of u and v, so you calculate it in this way that we just talked about. Right-hand side is magnitude of u, so square all of the coordinates, add them, take the square roots. Same for u, same for v. And then multiply by the cosine of the angle between the two vectors. So if you have vector u and you have vector v, and they have an angle of theta between them. Let me make v a little longer because I think that helps illustrate my point. Then the dot product is that value, right? It will be magnitude of u, so this length, magnitude of v, so this length, multiplied those two, and also times the cosine of the angle theta. Now the way to prove this, I can prove this purely algebraically to you if you want. The way to prove this is as follows. Look at this vector right here, okay? What's this vector right here? So if I call it w maybe. If I add vector u plus vector w, maybe keep it blue, vector u plus vector w, then that gives me vector v. You see that? U plus w equals v. That's because if I just start from this, follow u, tail to tip, and then w, tail to tip, I end up at the same spot that I would end up if I had just followed v. Okay? So this is vector addition geometrically. Okay, that's the first thing. That means, of course, that w, if I take u, move over to the other side, is v minus u. Okay? So that's w. If you use the law of cosines on this triangle, I'm trying to make the cosine show up, right? The law of cosines tells me this. Magnitude of w squared equals magnitude of u squared plus magnitude of v squared minus 2, and then magnitude u, magnitude v, cosine of the angle. So again, law of cosines on this triangle is going to tell me that this thing squared equals this squared times this, plus this squared, excuse me, times, or minus 2, this side times the cosine of the angle. If you don't remember the law of cosines, you can go back and review it. But the right-hand side is already kind of close to what I want. You see this here, right? But the left-hand side, if I calculate the magnitude of w squared, that will be the dot product of w with w. And as you know, w is v minus u. You can do the dot product of v minus u, v minus u. And I haven't proved this. I haven't proved this at all with you, but the dot product does obey the distributive property. So you can do v with v, v with u. So v magnitude v squared, because dot product v with v, minus dot product v with u, and then minus dot product u with v, plus magnitude v squared, magnitude u squared, like so. So basically what you're doing is using a minus b squared is a squared minus 2ab plus b squared, but with vectors instead, right? You see this first square, the second square, and these two, they're the same, right? Multiplying two vectors with the dot product doesn't change anything about its order. And then you get to cancel this on the left side with this on the right side, this on the left side, this on the left side with this on the right side also. So these all cancel out because, again, I'm calculating this, right? So what that gives me is that negative 2 u dot v equals negative 2 magnitude u magnitude v cosine of theta, like so. You cancel the negative 2's, and you're good to go. You get the equation that we were talking about before, yes? So that's a proof. It's pretty short. It does use the law of cosines, though. What's also interesting about this, if you go a little deeper, is that you get to, if you isolate the cosine, divide both sides by the magnitudes, then you'd get that the cosine of theta is u dot v divided by magnitude u, magnitude v. And so by taking the arc cosine or the cosine inverse on both sides, you do get this formula here. So these two are equivalent as long as the angle is between 0 and 2 pi, 0 and pi. So we're not going to be using angles that are greater than pi here. If you have two vectors, u and v, there's always this angle between them that's less than pi, and there's another one that's greater than pi, right? Maybe both of them are pi, it doesn't matter, right? But there you have it. Always going to choose an angle in this range. So this is totally fine. And we can use this formula to find the angle between the two vectors. So I'm going to solve an example. I actually want to save this. So I'm going to move this down. I didn't plan to use this formula at the beginning, to prove this formula at the beginning. So let me go ahead and solve example 13 there. So what we want is we want to solve or find the angle between two vectors. Basically, I know theta, that angle, is the arc cosine of u dot v divided by magnitude u times magnitude v. That's all I'm going to do, just apply this formula directly. And I'm going to need a calculator for this. So first of all, I'm going to calculate the dot products. So it will be 1 times 0 plus negative 4 times 2, and then 1 times 2. So that's the top of the fraction, right? The dot products. The bottom of the fraction will be magnitude of u times the magnitude of v. So I have to calculate that. The magnitude of u is the square root of 1 squared, negative 4 squared, 1 squared, adding all of these. So it's the square root of 1 squared, negative 4 squared, plus 1 squared. Okay. The magnitude of v is the square root of 0 squared plus 2 squared plus 2 squared. So it will be, maybe I gotta expand this a bit. Square root of 0 squared plus 2 squared plus 2 squared. Scroll back up to see if I didn't miss anything. 0, 2, 2, 1, negative 4, 1. Okay, looks fine. And the rest is now algebra. Actually, I forgot something. Hope you caught it. Forgot that it was the arc cosine. And by the way, if you ever want to break this task down into smaller parts, that's totally fine too. Just find the dot product first, find magnitude of u, find magnitude of v first separately, so those three things, and then toss them into the formula and then find the arc cosine. So it'd be 1, 2, 3, 4, 5 tasks maybe for you to figure it out. Dot product, magnitude u, magnitude v, toss into the fraction, and then arc cosine, so 5 steps, right? So this will be, again, the arc cosine of this whole fraction. Let's calculate the top first. 0, negative 8, and 2. So this will be negative 6 at the top. And then the bottom, this is the square root of, I thought it was 9, but it's not, I'm mistaken. This is 16 plus 1 plus 1, so it's 18 times the square root of 18 times the square root of 4 plus 4, so the square root of 8. Like so. We're talking about the arc cosine. So the angle whose cosine is -6. This is 9 times 2. So, and this is 4 times 2. So this is going to be 3 root 2 times 2 root 2, like so. Gotta move this down a little further. We should have planned this better. So it's going to be the arc cosine. All this that I'm doing is sometimes unnecessary. So you have -6, and then 6 times 3 times 2 is 6, and root 2 times root 2 is 2. I feel like I've made a mistake somewhere here, but I'll trust that you'll catch it for me. If I have, let me see. 1, 0, -4, 2, 1, and 2. 1 squared, -4 squared, 1 squared. So that's 16, 17, 18. Square root of that. And then 0, 2, 2. So that's 4, 4 is 8. And 3, 2. I don't see the mistake. Oh well. These cancel, and this will be the arc cosine of -1/2. And now I can go, I thought I was going to need a calculator, which is why I thought I made a mistake. Maybe I still have, but this is still too good to be true. I couldn't find the mistake, so I'll just act as though that's the correct answer. And what's an angle that you know whose cosine is 1/2? You know that the cosine of 60 degrees is 1/2. But because this is negative, that means you need to live in quadrant 2. You're always in those 2 first quadrants for the arc cosine, again, between 0 and pi. So that means your angle is not going to be 60, but 180 minus 60, right? So 120 degrees. So just found the angle between the 2 vectors is 120. So that's pretty powerful stuff. Finding an angle between 2 vectors without having to draw them. I think it's pretty amazing. You know, especially if you're in dimension 3, if you think about things a little deeper, and I like to do this. This is something that you can easily add a 4th coordinate to. So you can do x, y, z, w, and talk about vectors instead of an R3 and R4. Right? So in dimension 4, vectors in dimension 4. So you could just add a w1 times w2 here if necessary. And amazingly enough, you can still find the angle between 2 vectors in dimension 4 by making the same calculation, just adapting, adding an extra term for the dot product and for the absolute value, for the magnitude of the 2 vectors. But we're not going to do that in this video. All right, now let's talk about this. This is a type of problem that's classic and that you can solve very simply using the dot product. If 2 vectors are perpendicular, meaning 90-degree angle between them, then the dot product is 0. And the opposite is also true. If the dot product is 0, then the 2 vectors are perpendicular. Right? This is also called orthogonal. So this is a word you're going to see at times. Don't be scared. If you see that word, it just means perpendicular, also means 90 degrees. And going back a bit to this formula, it's kind of clear why. Now, if theta is 90 degrees, the cosine of theta, the cosine of 90 degrees is 0. So clearly, the right-hand side of this is 0. Right? You're multiplying 3 things. Of course, if this is 0, of course, the whole thing equals 0. Yeah? So the dot product is 0. Now, if the dot product is 0, so the other way around, then the only way for that to happen is if the cosine of the angle is 0 also, because this is the magnitude of a vector, this is the magnitude of another vector. This can't be 0 unless the vector itself is 0, but in that case we also say that it's orthogonal perpendicular. So the vector 0, which is the vector 0, 0, 0, is perpendicular to all others. That's fine. All right, now let's use this to our advantage and try and solve for a here. Give myself a little more space. And find whether these vectors are orthogonal, perpendicular, or neither. Or, excuse me, orthogonal, parallel, or neither. So first attempt here is to do the dot product of a and b. So that will be 4 times 3 plus 5 times -1 plus -2 times 5. So that's 12 minus 5 minus 10. So that would be -3. Because this is not 0, I can immediately say they're not orthogonal, not perpendicular. The angle is not 90 degrees, okay? And then when that happens, I can go and just find the angle between them to see if the cosine of that angle, right, will be either, so for the vectors to be parallel, then either a and b point the same way, so have the sort of the same direction like so, or a and b point opposite directions. In the first case, the angle is 0. Cosine of 0 is 1. And in the second case, the angle is pi, and the cosine of pi is -1. So I can find magnitude of a, magnitude b, multiply, divide, whatever, see if the answer is either 1 or -1. And that will tell me whether these two vectors are parallel or not. So let's try it out. Magnitude a will be root 16 plus 25 plus 4. Okay, so root 45, right? 45 is 9 times 5, so this is 3 root 5. And then magnitude b is root 9 plus 1 plus 25, so that's root 35. I have no hopes of this being pi, but I'll do the math anyways. Cosine of theta will be 3 root 5 times root 45, times root 35. So this would be -3. I'm going to do this. This is root 5 and root 7 times root 5, like so. 35 is 7 times 5. So these 5s together give me another 5. These root 5s together give me another 5. Those 3's cancel. So I'll get -1 over 5 root 7. I don't have to finish. This is not 1 and not -1 either. So they are not parallel. So the answer is that they're neither parallel nor orthogonal. Okay? Right. Now let's go to B. Let's do B here. Same thing, u dot v. That will be 9 times -2 plus 3 times 6 plus 0 times 17. This is -18 plus 18 plus 0, and this is 0. So they are orthogonal or perpendicular. It's the same thing. I don't have to check parallel. There's no way two vectors are orthogonal, perpendicular, and also parallel, right? If I have vector u pointing in a certain direction and vector v pointing at a 90-degree angle direction, then there's no way they're also going to be parallel. Parallel is this, right? Don't need to check for parallelism. Now let's talk C. I'll move D a little bit further down, and I think I'll be done. These are my last two examples. I'll do the same. I'll do U dot V. It's negative 8 times 6 plus 12 times negative 9 plus 4 times negative 3, right? Again, this is the ijk component form of the vector. So this is the same as vector negative 8, 12, 4. Vector U is, because we're remembering that I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1, like so. And so we end up with this representation for U, a similar representation for V. And so just double checking that I have the numbers in the right place. Seems like I do. So 6 times 8, first of all, is 12, 24, 48. And then 12 times 9, that's 12 times 10, which is 120. Minus a 12, it's 108. And then minus a 12, everything negative. Too bad. But cool, I got to combine these into another 120 because I took a 12 out to make 108. I'll put a 12 back. So that's 148 minus another 120. So that's negative 168. Not the number of my dreams here, but it is what it is. And so definitely not perpendicular, not orthogonal, because that would have to be 0. And if I just move this a little further down. Now I'll try for parallelism. I wonder what I can do about this. I know what I can do, but I'm trying to make you think about it, right? I've looked at this before. I'll do it, right? But then I'll also show you a different way to save a little bit of work. So I'm going to show you how to blindly do this. Just do magnitude of U, and that would be the square root of negative 8 squared, 12 squared, 4 squared. That's the square root of 64 plus 144 plus 16. Maybe combine these first to get, what's that, 70, 80 plus 144. So that will be, is that 244? 6 plus 2, 224 maybe? 224 it seems like. Yep. And then magnitude V would be 36, square root of 36 plus 81 plus 9. So combine these maybe to get a 90. And then that will be root 90 plus 31. So that will be 121. Nice, this is 11. Cool. Double check that I'm not just wishful thinking, forcing the numbers to work together. Double check. It's 90. Seems fine to me. I wonder if 224 is a perfect square. Would it be one? Maybe 18 is probably too much, right? 18 squared equals 224. I think probably not. So 64, 6, 8, and 6. Right, is that right what I'm doing? Then 18. So it'll be 4, 2, 1 is 324. Yeah, it's definitely way too much. 12, I already know it isn't. So, well. I've probably made a mistake somewhere. Let me check my math here. Give me a second. Yep, I saw it. I'm sure you saw it before me. Yeah. So how did that change into a 31 here as a 36? Again, wishful thinking on my part. So let me fix it. So 31 here is a 36, which then makes this a 126, and it's not 11. I was, again, trying to hopefully make it something easy, something simple. Yeah, I was wrong about this. But again, I'm making this too long. But 2, 2, 4. I can factor 2, 1, 1, 2, divided by 2. That's 56 divided by 2. This is 28 divided by 2, that's 14. Divided by 2, that's 7. Divided by 7, that's 1. So that tells me that root 2, 2, 4, how many 2's are there in pairs? They come out. It's 4 root 14, like so. If you multiply 16 by 14, you should get 224, and then the 16 comes out as a 4, the root 16. And then if you do the same with 126 here, 263, ooh, that's annoying, 7, it's 9, and 3, 3, 3, 1. So those two come out together as 9. So root 126 is 3 root 14. So if you multiply 9 times 14, that should give you 126. Right, so these are the two numbers. And I can kind of see why I was breathing heavily, because I didn't want to really do the problem this way. So that means the cosine of the angle is going to be, if you go back, negative 168 again. Negative 168 over 4 root 14, 3 root 14, which is negative 168 over, so 3 times 4 is 12, times, and then root 14 times root 14 is 14, and 14 times 12 should be 168. It is. So this is negative 1, which proves exactly that they're parallel. So again, not the easiest of calculations, but a calculation nonetheless that didn't force me to draw anything. Now, this is not the way that you should be doing this particular problem. I'll show you 2 ways to do it. I'll show you one way right now, and I'll show you another way later when I talk about the cross product on that separate video. Let me move this further down. Just to do like a retake of C. You can see that if you take vector u, look at this, multiply by 1/4, so that gives you a negative 2i plus 3j plus k, like so, and then multiply that by negative 3, you'll end up with negative 3/4 of u equaling positive 6i negative 9j minus 3k, which is exactly vector v. So that means you take vector u, multiply by some number, some negative number. So you multiply by 1/4, you just shrink the vector, take a quarter of its length, and then multiply by negative 3, so you revert the direction of the vector, and triple its length, so they are parallel. So again, this is not systematic, but it does help when you can see the multiplication here. Okay, they're parallel, and this is a definition, right? Vectors. If you're taking notes, just write this down. Vectors u and v are parallel only when u is a multiple of v. So you can take u, multiply by some number, maybe alpha or something, and that gives you v when alpha is a non-zero number. Oops, if it can't be 0. If you're taking notes, this is what to take notes on right now, on top of the problems, of course. Now let's look at D. I'm trying to keep those not too far away from each other. It's been hard, as you've seen, but they do look really similar. There is a difference between them, though. Look at this. Here, J is multiplied by 12. Here, K is multiplied by 12. And if you remember what with I, J, and K are, I is 1, 0, 0. J is 0, 1, 0. Alphabetically, K is 0, 0, 1. Then U will be, just plug those vectors in. This will be negative 8 here, but not 12 now, 4 here, and then 12 third, right? I'm not going to solve this problem on top of this. I'm just trying to really make you pay attention, right, to check that I think just by looking at this, I don't think these vectors are going to be parallel, right? So just double check the order, but go ahead and solve this on your own if you want. Just really, really pay attention to what letter is multiplying here.